Yes, I think now it's recording.
Yeah, I think I see
Um,
a notification confirming it. Yeah.
yeah, okay. Um, so yes, that's great to have you here today. Hello, everyone. Just would like to introduce our today's speaker, Simon. Simon Blondel is a geoscientist with expertise in seismic imaging, seismic data interpretation, soil tectonics, subsurface fluid migration, and sedimentary basin evolution. He studied geology at the Unilassal Polytechnic and applied geophysics at the Idea League between TU Delft, ETH Zurich, and RWTH Aachen. He recently obtained his PhD in applied geophysics at the University of Trieste, and he's currently doing a postdoc at the University of Oslo, where he investigates potential new CO2 storage sites on the Norwegian continental shelf. Um, Simon, the mic is all yours now. We're looking forward for your talk.
Thank you. I hope everybody can hear me well, and good afternoon, good morning, everyone, depending where you are. I think everything has been said about me, so I will directly go to the subject. And today I will present you some of the results I've obtained during my PhD at the University of Trieste and the OGS. And we will talk about the salt tectonics of the Mediterranean salt giant with a focus on the salt deformation within the Algerian Basin. So, like I said, this is the part of the work I've done in my PhD, and I've done this with Massimo Bellucci, which was back then from Ifremer and today working at Saipem. Sean Evans, back then at Imperial and nowadays working at University of Oslo. And my supervisors, Anandel Ben from University of Trieste and Angelo Camerlenghi from OGS. This project is part of a bigger project called Salt Giant, which is a European funded project under the Marie Curie agreement. I would like to talk a little bit about this to just present you the framework in which this project was embedded. And this project was had 15 students from all around Europe and the Mediterranean Basin dedicated to the understanding of the salt giant. So I will actually take that this an advantage to start talking about the Mediterranean Sea and the Mediterranean salt giant. So here you have on your right a map of the Mediterranean Sea and the seismic facies of the Mediterranean salt giant. This salt giant was discovered in the 70s during the first DSDP investigation in the Mediterranean Sea. And since then, we've discovered that this layer of salt was widespread around the whole Mediterranean Sea. And this isn't still nowadays a big subject of controversy to understand how this salt was formed and how it evolved. And this is why we created Salt Giant, to keep going on the future of this research. We were dedicated to the understanding of the formation of the Mediterranean salt giant, the deep life hosted within this salt giant, the geoeconomics and the history of science and technology related to offshore exploration and salt giants in general, and drilling hazard, which is the work package in which I was working. So just to show you very quickly the result of Salt Giant nowadays, we already published 18 articles. That's for the PhD students as first authors. And I'm sure there are many more to go. And if you want to know more, don't hesitate to visit our website, where you will find a list of some of our publications. And we also have some YouTube videos if you want to know more about this project. So now let's enter the core of this presentation. So I will start by introducing a bit the Mediterranean salt giants, because I am assuming that some of you maybe are not familiar with that area. And then we will look more in detail at the salt system of the central Algerian Basin. I hope I will have the time to discuss with you some work I haven't published yet that was part of my thesis on the distribution of salt tectonics domain in the Mediterranean at the end of this presentation. So the Mediterranean salt basin here is shaped by a distribution of fragmented plates, which are in subduction nowadays. Its origin go back to the subduction of the Tethys Ocean and the convergence between Africa and Eurasian plates. So you have, you can see here, you have these successions of subducting fronts, protracting arcs, and behind these arcs or in front of these arcs, you have basins where you can accumulate nowadays sediments. So we can distinguish between the Western Mediterranean Sea and the Eastern Mediterranean Sea, also if you want, with the Central Mediterranean Sea. And when I talk about the salt giants, I personally prefer to distinguish the West from the East. And this is for different reasons. First, just in terms of basin settings, to the east, we have quite an old basin from Permian to Cenozoic. This is the remnant, theoretically, of the Tethys Ocean. Yes. While to the west, we have much younger basins, Cenozoic in age, that opened behind the subducting fronts of the Tethys due to the rollback of the subducting plate, which was creating stretching in the overlying plate. But it goes a bit further. If we look between the west and the east, here on the front, you have a schematic section illustrating the differences between the west and the east. And you can see that in terms of facies, we can finish with a trilogy from the west with at least 3 layers of distinguished evaporite assumed, and the succession from the east, which is allied dominated succession. In terms of source layer, they are different. To the west, we seem to have a very allied dominated mobile unit, but it has never been drilled, so we don't know much about its lithology. But based on seismic facies, it's pretty transparent, so we assume it's quite allied dominated, quite pure in a way, not very dirty in terms of clastics or evaporites. While to the east, the Mediterranean giant is interbedded with dirty layers of clastic and evaporite, and this is confirmed through drillings that have been done thanks to the exploration for oil and gas there. In terms of overburden, it's different. To the west, you have this thick layer of upper evaporite, which is made of an alteration of clastics and evaporite. While to the east, you have this layer is much thin or absent, and you have only the plioquaternary overlying it, which is made of fine-grained plastic. And finally, the pre-salt. We don't know much about it in the west. It has never been drilled once again, but we assume it's the same to the east, so Messinian to Miocene, with eventually a rich content in evaporite to the west, by analogy by what we see onshore on the facies. And in terms of I will like you to keep in mind the differences in terms of source layers, because we will come back to that at the end of the presentation. This Mediterranean salt giant was formed during the Messinian salinity crisis. I will not go too much into details here because this is the whole core of the controversy, and I don't want to enter into this. It's not my whole expertise, and it's a real controversy. But let's say that what's assumed to be the correct scenario is that you have a tectonic activity around the Gibraltar arc, which is causing a restriction in terms of hydrological exchanges between the Atlantic Ocean and the Mediterranean Sea. At the same time, you also have a restriction between the connection with between the Paratethys here and the Mediterranean Sea. Due to this restriction in hydrological exchanges, the Mediterranean Sea becomes half enclosed, and evaporation with an excess of evaporation is causing a super concentration of ions until the deposition of the evaporites. This is gradual in several stages, but I will not enter in details about this. What we have to keep in mind for the studies for the next part of the presentation is that this is happening in a relatively quiet geodynamic environment from what we know. At that stage, the Mediterranean basin of the West I was talking about before have stopped their opening. And this is due to the fact that there is a big geodynamic rearrangement happening during the mid-Miocene, where a major block rotation creates a lot of strike slips along the subducting margins, which is creating some tearing of the subducting plates. And due to that, you start having slabbing of the subducting plates, and it creates these movements here of strike slip and eventually the uplift of the Gibraltar under the rebound effect. This is combined with the global cooling, hence why you start restricting the access on both sides. Since then, and from the moment you deposit the salt giant until nowadays, the geodynamic appears to be quite steady. We are in a steady strike slip converging settings, but you can have very different tectonic settings depending on where you are in the Mediterranean Sea. So if you stay in front of the active margins for the subducting arcs, you are in converging, those are inverted active margins, where you can, this is the Tel Atlas here in North Africa, the Apennines and the Danaride in the Adriatic, and the Calabrian arc and the Hellenid and the Cyprus arc here in the Eastern Mediterranean Sea. So this whole paracrine, you can assume that you have a global regional shortening happening throughout the whole Mediterranean Sea with some shortening pulses. And this is still active nowadays. This is testified by active seismicity in front of the active margin. We just saw that it's still pretty active in Turkey, but also recently, I think last year or 2 years ago, there was a big one in Algeria. And of course, the whole Apennine Dinaride. And also some volcanism, particularly behind the subducting arc in the Tyrian Basin and the Aegean. This is why the Mediterranean salt giant is such an interesting analog to understand early stage of deformation, because it's quite young, only 6 million years old, and it has evolved in a relatively steady setting. And you can assume that you could study the part in front of the active margins to maybe have insight on the early deformation for contractional salt systems, while you can study over systems like the Gulf of Lion or the Levant Basin to have insights on more extensional systems. All right, now we can focus on the Algerian Basin. This is basically a presentation covering the paper we've published with the co-author I mentioned before in basin research. That was reviewed by Francine Namarante and Laurent Minispichel, which maybe are here now. So connected to what I was just saying before, when I started investigating that basin, the whole idea was to see, okay, we are in front of an inverting margin, so there should be some sign of contraction, because the salt, being rheologically very weak, answers directly to this type of such an intense rate of shortening. But surprisingly, most studies I've seen in literature were describing mainly a thin skin deformation driven by basinward gravity spreading and gliding. Yet, theoretically, you should have accommodated based on some estimation of assuming nowadays GPS velocity recorded on the continents, more or less 11 kilometers of shortening, plus or minus 3 kilometers, in a north-northeast convergent setting. So my rationale was, can we actually see this recording? Did the salt record that shortening? And if yes, how, and how did it influence the basin? Here below, you can see a cross-section of the Algerian Basin, and you can see already that it's already known to be an asymmetric basin, and we'll see a bit more about that during the presentation. To do that, and this is the over part of my PhD, I've tried to reprocess some vintage legacy academic data that we had in the area. We've mainly focused on this red data set here, which is salt flue, because this is the highest resolution data set that we had here. But we also used other data set that I could access during data rooms at the University of Sorbonne in Paris. For the Northern African margin, I didn't have any data. So what I did is I used the seismic that was published in the literature, and I more or less basically copy-pasted their interpretation by citing them. I also used some gravimetry maps and earthmagnetic anomaly, but quite low resolution, to try to see if we could get some insights on the crust and the salt crust in general. And we used also high resolution seafloor bathymetry that was acquired during the acquisition of salt flue itself, to try to guide a little bit our interpretation of the salt dye piers in order to bridge the gap of 2D to 3D surface. And just to show off a little bit, this is an advertised publication coming. This is an example of how the salt flue seismic data was before and after I was done with the reprocessing. This is a work I've done with Jonathan Ford from the OGS. And this is our already accepted and should be, I hope, very soon proved, but it's taking a bit of time. And in the meantime, if anyone would like to go further into it, we are very happy to say that this data is open access. You can have it on Zenodo here. And once this paper is out, you could know more about how it's been reprocessed and what you have to keep in mind when you look at this data in terms of geology and geophysics. To do the interpretation of this data set, I followed the previous interpretation published on literature, and particularly also the seismic atlas of Lofi and al. On the Messinian salinity markers. I've picked obviously the top and the base of the salt. Those are a medium confidence. So it depends how well is imaged the base of the salt. For the top of the salt, we'll talk about this a little bit after. There are uncertainties about where to put the top of the salt because there's a gradational transition between the overlying reflective evaporites and the underlying less reflective salt. I've also picked the top of the evaporite, which is defined as the first strong kick compared to the overlying strata. We've tried to pick some basement, and by basement, we are in a very general sense that includes crystalline basement, pre-rift basement. So it could be central crystalline. It's not sure. We don't have a lot of constraint on that. And we picked two major soft peak regional horizons, which we call top PQ1 and top PQ2 here. Top PQ1 because it was quite regional and we could see some unlapping on it locally. And it was capping most of the salt dip here. So we thought it was a good one to map. And also top PQ2, which in that case is the boundary between the highly reflective Quaternary and the less reflective Quaternary. Here you have a view of some regional transects across the study area to illustrate the geometry of the basin. So what you can see directly is that this basin is very asymmetric with the deepest part in flanking the North Algerian margin, which is here. I hope you see my mouse. We also see that there are important lateral wave variation of the basin. As you can see here in barely 50 kilometers, we go from a pretty narrow basin to a much, much wider basin. This is more or less related based on the position you are with the thrust fronts, which are recorded at the inverted margin on the North African side. We see also here that the base salt relief is not as gradually steepening. We actually observe some major base salt relief drops, and that you have a preferential accumulation of the sediments in front of the Algerian margin, reflecting the asymmetry of this basin with the preferential subsidence in front of the Algerian margin. You just have a bit of water. So using this first cross section, we define 5 structural domains, a little bit more, but during this presentation, I will ignore the Balearic promontory area. And we define these domains based on the thickness of the salt and its overburden, the depth of the pre-salt, so here, and the type of salt structures that we observed. And one of the things we can see already from this zoomed out section is that these domains seem to be a little bit aligned with what we observe on the free gravity anomaly, which could reflect some different type of crust. We don't know what's the type of the crust, if it's very oceanic, like its journey suggested, or if we have maybe some more contrasting gradual continental thrust here. Here you have a view of our study area where we display the as inferred basement. And like I said, basement in general sense, including crystalline, volcanic, and pre-rift basement, and fold and thrusted basement, as you can have it there. And a few of the seismic lines from salt flue here with the interpretation we've made overlaid on it. And I would like to point your attention here first to this little perch basin. We'll see that one a little bit more in detail after that, which is landward dipping, as you can see, not dipping seaward. And also the base salt reliefs that I was talking about, that we see very well here on this 3D sketch, that define more or less the transition between the domains we delineated. So one here between the Balearic slope ramp and the Balearic slope, and one here along the transition zone that we call, that place we call the transition zone between the Balearic ramp and the Algerian fordip. And you can see here as well, again, very well, this change of thickness in the overburden, partially the plough quaternary, which suddenly thickens as you pass the transition zone here, reflecting the asymmetry of the sediment, plough quaternary sediment distribution. And we see also here that we have actually minor change in the thickness of the upper unit. It seems quite well distributed through the basin, and it thins down gradually toward the edges of the basin. You see it pinches out both on this structure here, suggesting that it was already present during the deposition of the salt, and along the slope that marked the transition to the Balearic promontory. So now let's zoom in a bit. And what I will do is I will go from the Balearic side, basinward, until the Algerian side, and we'll see the domains one by one. So first, let's have a look at the Balearic slope. Here, we're zooming it a little bit on that section, and I will come back to what I was saying before about the top of the salt. So you can see here that it can be eventually a little bit tricky. If you just look at that section, you could say that this is the top of the salt, because here we have a very nice reflectionless seismic fasces. But in reality, it's a little bit more complex than that, because these evaporites can change can disappear laterally. And if you look very well, I didn't overlay the interpretation, so you could see that, but some of the faults here seem to root on this reflector, and you do have faults here sometimes that go root on this reflector here, the big one. But there are different fault sets, and this led us to suggest that the top of the salt that we could here originally is better picked as this yellow horizon. Obviously, the best way to constrain that would be to drill it, but we would confident in doing this because we could make also an analogy with eventually the Levant Basin, where we do observe some intrasalt reflectors. And when we go toward the basin, if you keep an eye on it, you will see that it's much clearer to pick that one, because these reflectors will laterally change or disappear or are hard to track, while this one is always very clear to pick. So we would be confident it would be more coherent to do it that way. One here, you can already see that it's very interesting. The faults here show very low record of lateral displacement. So that suggests there is very limited gravity-driven movement of this. You do see here a little bit of turning, sorry. However, it's very mild, let's say it's a low amplitude. And we do see also as well, one thing I almost forgot, some thickness variation in the upper unit here, partially after this drop, suggesting that we had already some sort of movement during the deposition of this evaporite eventually. Now, if we look at this little perch basin, we see that we have a very thin layer of salt. Once again, small sign of lateral displacement, although we do see these lateral fields here at the pinch out. Here it's not very clear which direction could flow that, in which direction could flow that salt, because we only have the 2D, maybe eventually along that slope here. And we can see that this, the overburden here, we have a migration of the deposenters from here until there, suggesting a landward tilting of that block, proving that this is actually active. And we can see this as well by the faulting of the plough quaternary here. And now we'll keep this in mind, because we can see also this mass transport deposits here that suggest that we have some moments where you have tectonic pulses that could destabilize the sediments here. And you can see here, it seems to be just after the top PQ1 here in orange. suggesting some tectonic activity around that moment. Quickly, a last example of the Balearic slope. Once again, here you can see these thickness changes in the upper unit here. What I think is interesting in that slide is to see how bended can be the upper unit across these fault displacements. Here we see again these reflectors within the salt, but you can see they can pass laterally to non-reflective. And we can see when we try to follow the faults along the salt, the diapir's flanks, we don't see them root very deeper in the diapir, so we're much more confident in picking back upper horizons. And you can see here the crystal faulting above this salt anticlines or salt pillows. It's not sure. Once again, we don't see much evidence of salt gravity-driven salt displacements. You can see here there don't seem to be a lot of downturning. These faults show very small movements, record very small movements. Now we go into the Balearic ramp. This is separated from Balearic slope by this first important basal drop. Here we don't have a very good imaging of the pre-salt and partly the basement. However, we do seem to see some faulting and some basalt relief here that suggests a landward deeping pre-salt. And that could go well with the movement we see here. We can see here these salt mini basins which are sinking here under an expulsion under the salt, suggesting a salt movement going either that way and in that structure, or being exposed that way, basinward, basically. In here we have mostly in this part to the west of the study area, we mostly have salt anticlines or salt pillows. We're not really sure because we only have 2D. We can see they are often squeezed into the salt walls or pillows, with some potentially alloctonous top, but not very confident if it's very detached or not using our seismic data. We have a pretty high, low frequency of the folding with a structure every 1 kilometer. And you can see that there are some evidence of potentially some small amplitude salt detached thrust here, like this one. And yeah. Another example, here we go a bit eastward, and you can see that there seem to be more deformation here. At least the structures seem to be a bit more complicated. This is a good image to show how it can be tricky to interpret these structures using short offset to the seismic only. We have some reflections that could be out of plane or could be residual multiples of the reflection of the upper unit. And here what you see is once again those shortened, squeezed salt diapirs or wall here. I really like this one, which is very interesting because this one here really deforms the seabed and it forms a circular hill, let's say, on the seabed, and that's what drove the attention of scientists to drive the salt acquisition for the anecdote, because we were thinking it was maybe signs of mud diaperism, which is also something I investigated, but I didn't really like that theory so much. We don't have a lot of evidence saying it could be mud and very salt everywhere, so we're going for salt. And here you can see well that the upper unit, the whole roof from upper unit and playa quaternary 1 is arched above this salt structure, and very often above the regional level of the upper unit, which would be more or less here. And you can see that you have pretty much very hard structures here and some parts sinking quite low here. And notice also as well here that the whole upper unit and part of the playa quaternary unit is relatively constant in terms of thickness, suggesting that there was low to mild salt deformation during their deposition here, but most of it was deformed a bit later. One more thing before I skip. above the basal here, you can see that there seem to be potentially, and once again, we don't have a really great imaging of this basement, but we do sometimes have a good imaging of the basalt. There seems to be a correlation between the position of some salt structures, particularly the highest ones, and the pre-salt base relief. Moving basinward, we're about to leave from the Balearic ramp to the Algerian foredip. And this is a transition zone where you can see a bit both of the, between these two, we have a transition zone where you can see both of the characteristics of both domains. So I had to map that because otherwise it was a bit difficult to map a clear boundary between the two. And here you have a slide illustrating how complex can be the structures here along these transition zones. We have large, high salt structures. I have to say very often badly imaged with our seismic data sets, and we're not even sure we are completely going in a perpendicular direction across this structure sometimes. And here we see to the west that it's quite complex. We have this sort of asymmetric mini basin, very thick here, sinking into this salt, some very clearly squeezed salt diapese here with a detached eventually top. And we can see this two ramp here, or flaps, facing each other, bounding that mini basin here, suggesting there is still quite a strong active salt deformation here that is able to uplift this very thick of a burden. As we passed this transition zone, we enter the Algerian foredip. And here, like we saw before, there is a sudden thickening of the plioquaternary. And we have a much thicker of a burden, partially the plioquaternary, almost peaked another horizon here, but it was quite hard to follow originally. And what's right compared to the other domains suddenly is that the salt diapiers do not rise above the Messinian upper unit here, marked by the top here. Most of them actually are capped at this Messinian upper unit. So there is definitely a difference, and we can wonder why it could happen. And our first guess here, and we'll come back to that a little bit later, is that the aggradation rate in front of the Algerian in the Algerian foredip is too high for diapier rising rate to compete with it, and the diapiers get buried by this very high aggradation rate. This is another example. We are still on the west part of the study area. And here I just wanted to show this, for example, this salt detached thrust here that we see here. And also this very nice smaller wavelength folding of the salt that we interpret as polyharmonic folding, suggesting there was already some early deformation of the salt here in the Algerian foredip, but we didn't see much on the other side. Also here, if you look at it, you can see that you have thickness variation of the upper unit, suggesting that this was still active. This was active all the way during the Messinian, the late Messinian stage. Still on the western part of the area, just to show you these very nice structures that I like. I like these ones, which I saw in some publication can be called like mini basin. So it's sort of uplifted section of overburden above the salt here. And we can see below, as in the Algerian foredip, we have a pretty okay imaging of the base salt, except below the structures. And considering the quality of our seismic data, I decided to go for interpolating the two parts where I see the basalt as flat. But we could suggest maybe some basalt topography here. And we'll see later that recently a publication from Soto et al. Using better seismic with better penetration rate, that there might be actually some pre-salt topography influencing these structures in a thick-skinned tectonic way. Now we go east, and once again, when we go east, it's getting a lot more complicated. Here we have structures that we don't image very well with our seismic data. To image that, you would really need 3D and a very long offset records, obviously, because we interpret this as alloctonous salt sheets, and you can see that these salt sheets are laying on top or near the top. It's not very clear of the Messinian units, suggesting that they've been in place at least at that moment. And there is very interesting, contrary to the other part of the basin, where you could see wide upturning of the overburden along the substructures. Here, the upturning is confined really to the nearest radius around these structures, which we interpret as passive diaperism mainly. Once again, but here it's really interpretational. We think we might have some structures beneath this basement influence, pre-salt influence on the formation of these structures, suggesting thick-skinned tectonic, maybe. And this one is a bit in bonus because it's not part of my publication, so excuse me for it's not very well illustrated, but I wanted to show it. It's still to the east part of the study, and we have this huge salt body. I'm not sure exactly how to call that, and I did not present it because we don't understand it very much. It's really at the edge of our seismic, so we have no idea how far it goes on that side. We don't have a lot of seismic to constrain that. And it's definitely something I would like to see better, to understand a little bit, because you see it's not very deformed. It looks a little bit like the Eastern Mediterranean Sea in the way it is, quite cohesive, quite a cohesive body with diaperism, deformation above it. But it's all I can say about it. And if you want to see, we discuss it later at the end of the session, feel free. Now, if you look regionally, what we have seen that there seemed to be a correlation between the basal relief and the distribution of the structural domains. With this is suggesting maybe a bit of thick-skinned salt tectonics. We preferentially have high salt diapiers rising up to the seabed along the Balearic Rump, while in the Algerian foredip, except to the east, where we have these salt sheets and these complex structures, we mainly have salt diapiers that are buried beneath the plao quaternary. In terms of thickness, what we have observed is that the maximum thickness of the evaporites is at the foot of the transition zone, so actually quite at the center of the basin, not along the Algerian foredip. On the other hand, the maximum thickness of the plao quaternary is bordering the North Algerian margin in the Algerian foredip. And this might suggest that the bulging, negative bulging, or the foredipping really happened mainly during the plao quaternary in this basin. So based on that, what we suggest as a geological model for the Central Algerian Basin is a relatively quiet stage during the Messinian salinity crisis, with mostly passive diaperism under the weight of the upper unit, which is causing some expulsion of the salt into some passive salt diapier at that moment, except along the Algerian foredip and partially to the east. We could have already some compression that was recording with this multifold small wavelength salt structures we've seen in the Algerian foredip before. And then from upper unit to the top plao quaternary one, we have constructional pulses, and we identify at least two in that stage. The one at the end of the upper unit deposition, which is causing the expulsion of these salt sheets in the Algerian foredip, and one during the plao quaternary around top PQ1, which is buckling and folding the whole pre-existing overburden above salt cord dye piers, and which is squeezing the pre-existing dye piers that were formed passively before. Potentially, we think that this contraction folding, partially the top PQ1, might reactivate some faults along the Emil Bodo Balearic margin area, as recorded with the mass transport deposit that we've seen before, and the general uniform thickness of the, that's it. Then from this moment to nowadays, there seems to be less tectonic loading on the whole system. And it looks like we mostly have some diapyrism, we think active, but dominantly gravity driven, with possibly still in the background a mill regional shortening, which is allowing some structures, partly where the overburden is very thick, to still uplift their overburden. We definitely have, during that moment, and I forgot to mention that before, because of the high aggradation rate in the Algerian foredip, we sort of have a shift of the salt deformation toward the Balearic margin, because the overburden is just too thick and too resistant along the Algerian foredip. And that's what we are seeing here with this high dye piece here. What we see that the dye piece here are not able to truncate higher in their overburden. And that's it. So what we have seen is that in the central Algerian basin, the salt focuses strain applied by the regional shortening along the Algerian margin, and it acted mainly as a decolon, absorbing part of the strain, even though it's not enough to sometimes accommodate the strain. So we have this thrusting here. And after the Messinian, there we have some high aggradation rate, and you have a competition between salt dye pier rise and aggradation rate. And where it's happening, when you have tectonic pulses, you manage to still make some high salt deformation, because nowadays the Algerian foredip is too hard to sort of deform the overburden. The salt deformation has shifted outward away from the active margin. And that's what I've just said, I think. Yeah. To go a bit broader in terms of for the study, you can see here to the west, the Western Algerian margin is very different. And we don't see many diapyrism here. The basement seems very flat here from what we've seen. Unfortunately, it's very low quality, and I didn't have time. I got this line very late in my PhD, so I did not include it in my study. But that would be worth it to extend it to the Western Algerian basin. And like I said before, recently as well, Juan Soto published a paper, which I invite you also to read, complementing a bit this study with this North African margi part, confirming that there is potentially some thick skin tectonic, and confirming potentially this trace fault relief that we have seen for our case in the Algerian foredip. And now in terms of time, I'm not sure how far can I go. Do I still have 5-10 minutes? I'm assuming that yes. And in this part, I will present you something that we haven't published yet, because it's really something I've done to try to compensate the COVID effect of my PhD, because I was supposed to do the study of the salt deformation in the whole Mediterranean basin. But because of COVID, I could not go into data rooms, and I was a bit forced to stay only in the Algerian basin. And so what I've done is I've went through all the literatures I could find to try to sort of map where we can see extensional, transitional, or contractional salt tectonics, and try to sort of map that. Obviously, it's very blurry in terms of where is the boundary, so that's why it's not yet published. And I've overlaid that to a plioquaternary distribution of in the Mediterranean Sea to try to see where can we have dominantly sedimentary loading on the tectonics. Try to understand a little bit this. No, before we go in details, once again, I was introducing it a little bit before when I started. You can recognize more like classic and the most studied area in the Mediterranean Sea, which is the Gulf of Lion and the Nile Delta 11 Basin, where we have these important sediment inputs from the Nile and the Rhode Delta. And this, we'll see this a bit later. They seem to display quite classic, let's say in a way, passive margin characteristics, while we have in front of it, partly in the Western Mediterranean Sea, these very abrupt margins, and this is true for the VAR, Corsica, Sardinia, and the whole North African margin, as well as the Balearic margin, where we have a narrow, if not sometimes inexistent, extensional to transitional domain, and a really quick transition to the contractional domain. Here in the Algerian, we definitely, as we just showed, have an influence of the inversion structures along the North African margin, with quite a complex multi-directional flow already of the salt, which could suggest we are in an early stage that could be an analog to the Cyprus arc, where we have a much more advanced thrusting of the thrusting in general. If we go in details, let's start with the more easy one to describe because we don't see anything on seismic. It's the Calabrian Ionian Sea part, because you are in a very advanced stage of the progradation and the subduction. So all the salt is imbricated in the accretion prism and might serve as a lubricant for the progression of the gradation prism. Here to the east, we have this, like I said, the Cyprus arc, which could be a more advanced stage of thrusting, but could be analog for a further stage of the Algerian margin, where we have some kind of isolated perch basin in which salt flow toward the center of the basins, but we have apparently very thick skin tectonic, of course, above these structures. And the 11th margin, where we have apparently a more, actually into literature, a relatively classic distribution of the salt domains with an up deep extensional domain, a transitional domain, and a down deep contractional domain. And then when we go to the west, it's more or less the same pattern for the Gulf of Lion. You can see here this extensional domain with a nice rollover, so detached normal thrust, and this more control in the dipiers. And the example we just saw in the central Algerian basin. And while doing this, what struck me is the difference between the east and the west. And partly if you look between the Gulf of Lion and the Levant Basin, which are a bit more comparable than the rest of the other margins, we see that in the east, the salt managed to stay in a quite cohesive, unique salt body. While to the west, this is highly deformed. You have really high salt structures, really high salt bodies. And I've done a bit of reflection in the thesis on trying to understand that. And my first guess was the rheology. As we said before, in terms of seismic facies, they're quite different. In the east, we have drillings confirming that this salt is quite dirty with beds of clastics and evaporites in it. And this probably has an influence on the rheological behavior because this creates different partitioning of the way the salt accommodates the strain. Maybe this is why it's harder here to create high salt dipiers. In a way, it's less viscous. It's more like a multi-layered unit. But to the west, if we have really that pure body of a light, once again, we don't know. We have no drill. And maybe this is why this one is more prone to deform and create this high salt structure. In a way, it's a bit less viscous, maybe. Yeah, sorry, that one is what was for a surprise. So that would be my first guess, because in terms of loading, they are quite similar. And another one that could potentially explain that, but it's really to throw oil on the fire before discussion, is potentially thermal loading. As we said before, the west and the east are very different basins in terms of settings, because the west basins are much younger, and the surface heat flow is 2 to 3 times higher to the west compared to the east. So maybe there could be a proof of an effect of thermal loading on salt tectonics there. Impossible to say with what I have, and I think that would need a lot of modeling to go further and really a lot of data sharing to start bridging a gap in mapping the tectonics in the adometrian scales. And I think that's the insight for people that will keep studying the Mediterranean Sea. And I'm very happy to discuss that if you want. Thank you for attention. I hope I wasn't too long and I was clear enough, despite my clumsy English sometime. I would like to thank, of course, the European Union for funding this PhD and the whole Salt Giant project. Shearwater for providing us the software for processing the data, Schlumberger for providing us Petrel for interpreting the data, and the University of Trieste for providing high computing power for the whole processing part. Thank you.
Thanks, Simon. That was a really good talk. Really enjoyed that. Thanks for the presentation. We've got a few minutes for questions, and we've got plenty of questions coming in, so we'll get stuck in there. Our first question is from Salim Shakur, and he's asking, he's got a few questions actually, but his first one is, would you consider the Gulf of Mexico as a salt giant? And if so, what are your criteria for applying this name?
I think so. I don't know the Gulf of Mexico at all, personally. The way we describe salt giants is kilometric scale and like more than 10 kilometers accumulation of salt, evaporites and salt, partly with allied immunity in one. So in that case, I think the Gulf of Mexico is one of the typical salt giants. We know it's a lot more studied than the Mediterranean Sea, actually.
Great. Selim's next two questions are kind of linked. He's asking, it seems that the subsalt, according to your slides 17 and 19, it appears that your subsalt basement configuration has an impact on the salt diaprism, has more of an impact, sorry, on salt diaprism than the thickness of the supersalt sedimentation or the supersalt sedimentation rate. What are your thoughts regarding that?
Yeah, we definitely see a correlation, but we're not, that's what I was saying about it. We have a very low imaging, quality of imaging of the pre-salt. So that's why in the paper, we don't emphasize this, because anyone could say, hey, but your seismic would not allow you to say that confidently. We do see a correlation. And I was also not very sure how active this pre-salt relief was. Could it be very reactivated sometimes with the Placosmian in the Messinian to really influence the salt, or is it just quite passive and you just have these steps in the pre-salt? So that's why I didn't go further. What I'm pretty confident about is the influence of the overburden in the Algerian foredip, because regardless of this, we see that the salt diapirs just cannot keep rising in that place, nonetheless of the active convergence from the North African margin. In the basin itself, so when we are between the Balag, oh, maybe I should show that, sorry. My head it's clear, but just slide this. I'll take just the 3D view so we have a good view of the whole thing. We discuss that. There it is. What was I saying? Yeah. So when I was seeing this transition zone, one of my guess was that maybe also because of this high aggradation rate in the Algerian foredip, you have an expulsion of the salt against this pre-salt relief, and maybe that's why you have these high complex structures. Now, how active are these structures? I really cannot say. As you can see, we sort of inferred a bit the pre-salt geometry here. What we see here for sure is that they do have an influence on, because this one is rising, but nonetheless, it doesn't seem, the salt seems to glide here and more or less in the spread or glide in the same direction, and we don't seem to see a major impact here, except this folding, but you see it's not very coherent along the whole thing. One also downside in our study is I don't manage to grasp much with the limited 2D dataset we have, the strike slip component. So when you try to link a bit these structures, it's really challenging in 2D. So that makes it a bit more difficult to constrain how much the pre-salt relief might be active and might be thick in the deformation thick skin. And that's why we focused a little bit on the overburden.
Nice one. I really like this 3D figure as well. It really works really well to show the geometry of the area. Very nice.
Thank you.
Our next question is from Martin Reyes. He first says, "Nice talk, Simon." He would like to know, what was your criteria to ignore some of the reflections below the soft bodies? And sort of how do you constrain, this kind of links into the previous point, how do you constrain the basement to make sure that your geometry is more or less regular?
Sorry, was it for the top salt or the reflection within the salt itself?
Your subsalt basement, what was your criteria for sort of building your basement shape and your basement reflectors, and which were real, which weren't real?
Here on the margin itself, we do see it very quite well. So that was easy to pick. Where it was really challenging, it was actually in the Balearic Rum. In the Algerian foredip, we do see a reflection that we can follow here. Like I said, in some places, it's the place where I showed this potential base pre-salt relief. Because we had a very limited imaging, I sort of ignore that, because the first time I was showing this pre-salt relief in presentation, people were a bit skeptical. So I decided that with the limited penetration rate of our seismic, we just had to assume the simplest fit scenario here. Here we do have some vision of the pre-salt, some very faint pre-salt reflection, and we try to pick that, more or less following also a bit the base salt reflections. So there's definitely a little bit of, that's why I was saying at the beginning of the presentation that we are not super confident in the pre-salt topography. However, we do see for sure these base salt drops, because the base of the salt is much better imaged than the pre-salt reflector itself. And this is connected to the question before, why we didn't go very much further and too much in details in the pre-salt structures influence, because we don't have a lot of constraints of, we don't have a lot of confidence on that. So that's why we focus on the overburden.
Nice one. Just checking, we're coming up to about 3 o'clock GMT, I guess 4 o'clock your time. You're happy to go on there's a few more questions coming up? Happy to go a little over time?
Yeah.
Excellent. Our next question is from Sophia and Jazar. Do you believe in the existence of hydrocarbons in the area? And if so, what do you think the petroleum system, what would be the components of that petroleum system?
Yeah. Personally, maybe. No way. So we do have these fluid indicators in the Algerian foredip that prove that there is an active fluid circulation. The trick here is that it's inverted margin, and as you can see here, we have a lot of volcanic activity that goes based on sampling done on these volcanoes. It was done during the Quaternary. So that means that the fluids we observe are not, it's not sure if they are thermical fluid done by an organic source rock maturing and exposing hydrocarbon. It could be related to the volcanic activity, particularly when you go here. And to the east of this study area, there is a basement high called the Hannibal High that could also be volcanic deep in the basin. So the thing is, there is maybe hydrocarbons. We do see that. If there is if these fluid indicators are hydrocarbons, that's where it gets very interesting, because it means that either they are sourced within the upper unit, which, I mean, maybe, but I don't think there are a lot of proof for. I mean, I did read a paper, I think it's ELS 2006, that tried to model that for the upper unit to see if it had a rich potential. It has good organic matter content, but it's probably not mature enough to make gas or hydrocarbon at that depth. So it could actually come from the pre-salt, and in that case, that means that these fluids are able to breach through the salt, and it's a bit surprising, but it's actually observed in the Eastern Mediterranean Sea. So in that scenario, the only problem is that we have absolutely no drillings in the whole Western Mediterranean Sea that goes through the salt and beneath the salt. So we have very little constraint about this potential for hydrocarbons. And I don't think it will go any further because it's just too deep in terms of water, in terms of the pre-salt and the water depth itself to make this, well, we'll see how expensive can get the barrel oil, but it's just economically not interesting to go further in the Algerian Basin so far.
That's one. So I guess, yeah, just a follow-up question for me then. Has there actually, do you know if there has been any exploration in the area, or is it completely unexplored?
Offshore, yeah. There was a little bit of offshore exploration, but not in the deep Algerian part. They have done, I think they have a map of the wells. You have these wells here called Algerian, Ardu, and Abibas, which were, if I remember well, targeted for oil and gas exploration. But in these wells, they do go through the whole evaporites. There is no salt in these basins, so it's not a super good analog for us to study these wells. And
cool.
So far, all of them were dry, if I remember well.
That's one. Our next question is from Juan Soto, who says, thanks for a great presentation, and he appreciates the shout out. He has two questions for you. The first is, what are your criteria for picking your top salt? I know you went into it in a bit of detail at the start.
Yeah.
In many cases, you have strong reflections within the salt, but only the mini basins. And then his second question is, what is the influence on the salt tectonics, basically between the oceanic and the continental crust in the area?
Hi, Juan. Because I know Juan knows very well the place because he studied this extensively as well. For the top salt, yeah, it took me a long time before I could be happy with my top salt to decide whether I pick even the lowest reflectors, or if I do say, okay, this is the strongest reflector I have, so I should pick this one. Could be because if it's the strongest, it's definitely a big contrast in terms of petrophysical properties and lithology. And the advantage that I had is that I did myself the processing of the seismic. So I have access to the pre-stacked shots. And when you look at the reflection before migration, you can kind of have an idea of what's happening. It's still tricky because you have an alternation between clastic and evaporites. So it's not very clear sometimes what can be a multiple of the upper unit and what can be a real reflection from the lithology. As I said here, when you go regionally, the one that is easy to follow is this one. And some of the faults on here, it's a bit more confusing, but you can see here that these faults, for example, you cannot really route them to reflect to the reflectors which are beneath. And so that's why I decided to stick to that one. That was easy to study because we have this pattern of reflection with one strong amplitude that marks the top of the evaporite, this very, very strong regional kick here, which is marked by the dark green horizons. And then we have a less reflective package, and then this two couplet of very strong reflection. And this is observed almost everywhere regionally, although when you arrive in the Algerian foredip, we have lateral fascist variations, which makes it a bit tricky. But this kind of pattern is easy to follow and could allow us to pick this confidently, while this peak horizon is really variable laterally. So that's why I think it's actually more likely that this is inside the salt and some maybe lateral variation. Here we are at the margin, so we're probably the closest to some sedimental detrital input. Particularly here you have a canyon that feeds a lot of sediments. That could explain why we have some clastics interbedded in the topmost part of the salt, why we come back to more at the end of the worst part of the crisis. But when we go in the basin, maybe more away from the sediment influx, we lose this reflection because the salt is more influenced by dirty clastics and evaporites, let's say, marginal evaporites, let's say. For the influence of, what was the second question? Sorry, the influence of salt tectonics on crustal
on the oceanic crust versus the continental crust.
Due to the fact that there is a lot of uncertainties on the crust of the Algerian Basin, we assume it's oceanic, like the rest of the Mediterranean Sea on the scenario, and based on the result from tomography, it makes sense. What we see here with this base salt relief drop is there's definitely some differences in the nature of the crust. Could it be some very stretched continental crust here at the transition between the Balearic margin and the Algerian Forde? I have the feeling, from what I've done more regionally with the whole Algerian Basin, that you can compare a little bit the Algerian opening to some very strike slip oceanic basin, maybe like the Gulf of California or the Gulf of I forgot the name, in Antarctic, south of Chile. It's another very curved subduction front. And if you look at them, you can have very tight and offsetted pieces of oceanic crust during the opening because it's really a strike slip transtensional basin. And I feel like it might be the scenario here, and only the Algerian Forde might be the oceanic part, if it is oceanic. And this part might be a very stretched, thinned continental crust that goes all along the Balearic margin. At least based on that study, for sure, I don't think we can put the oceanic crust right at the foot of the Émile Bodo. It has to go at least here or here.
Nice one. We've got a few people congratulating you on an excellent talk. Julian App says, excellent talk. Thank you.
Oh, really? Because I was struggling a bit with my English, so I'm happy if people found it clear.
No, it was perfect. Really, really clear. Really clear. Manasaho also says, a very nice presentation. Kudos. Frank Peel, again, it's a great presentation. He has a question here. Your line shows strong evidence that withdrawal and diaprism started during the upper unit, during the period of overall deposition. Do you have any thoughts on how this might have affected evaporite deposition? For example, by creating local topography in the withdrawal basins?
Yeah.
And could these have become brine pools or lakes during extreme periods of extreme drawdown?
No. I don't think I can bring a lot of answers to this because we only have 2D data, so it's hard to see very local facies variation, lateral facies variation. I was just talking about it before. Regionally, I can easily follow this pattern of reflectivity in the upper unit, which would fit with this idea of being arbitrarily driven sequences of humid clastic rich sequences with dry evaporate dominated sequences, all regionally. Locally, I don't see many lateral, like I said, with this very sparse 2D, I think it would be difficult. In the area, I think there is only this data set, salt flue, that has a resolution good enough to try to map this. The one big difference I see is in the Algerian Forde. And maybe it's because it was already deeper. So in that case, you might have a different type of evaporite due to the layering of the Mediterranean Sea here. Not sure. We're doing some more investigation on this by comparing it with what we see on shore. But it's not, we don't have a conclusion yet. And I think keep tracking on what's happening with Giant, and maybe we'll be able to give more insights on that.
Nice one. Yeah, it looks like there's lots of really cool research coming out of the Salt Giant team in the next few months and years. You happy to keep going? There's a few more questions coming in.
Yeah, sure. Yeah.
Excellent. Our next one is kind of I guess, a comment from Jafar Hassanpour. Nice work, Simon. He really enjoyed your talk. In the seismic lines you showed, there is some huge diapirs with very narrow upper and wide lower parts, with very thick salt, a very thick remaining salt in the interpreted source layer. He thinks it's a layered evaporate sequence, but the mobile part is only in the lower section. So Jafar is wondering then if it makes more sense to interpret it as a more layered sequence and have only the lower unit be mobile and not maintain. I guess you can see it kind of on the left or the north side of your sections there, the quite thick source unit beneath very, I guess, mature salt structures.
Yeah. So if I understand well, the question is about the whole salt body we interpret itself, because we do see some reflection within it. If we could separate it between an upper, less ductile salt and a lower, more ductile salt. This, I think it's still based on where you put the top of the salt. And if you follow this, criteria, you could actually say that this one is a little bit more brittle. However, and I think that's what I show here, it has quite a remarkably ductile behavior when you see how it deforms itself. I think it's an interesting lead to suggest that there is maybe an inner, more ductile, pure halide salt layer here, and that place might have a partitioning of the strain between this very ductile layer and a more brittle, rigid layer. Truth is, we don't have the insight to say that for sure. And when you follow the fault, the crestal fault, and the fault you observe on the seismic, you cannot really see them going through this upper, more reflective part. I mean, it's hard to say, of course, for sure. So that's why I think it's more coherent to say that the top of the salt, the ductile part of the salt that moves, is here and not lower, because it would make it challenging in terms of salt interpretation, how they route to the salt itself. That being said, the only way we can really know for sure, because I see what you mean. When I did the interpretation myself, I was tempted to put a very thin salt and go very low, saying that only the ductile part is very transparent part. But we have to keep in mind that we can have reflection in the salt, and it can still be ductile, like in the East Med. And I think the only way we will be able to know if we finally manage to drill it one day in the very far future, apparently.
Yeah, we'd always love to get out and drill some, but I guess, yeah, you can, in places like offshore Brazil, you can see lots of layering in the salt there.
Yeah.
Shaza Haidar says, a nice presentation. Thank you very much. John Davies has a question. Have you considered the balance of tectonics and the effect of dewatering of rapidly deposited sediments dissolving the underlying salt, thus increasing the space for more sediments? The near salt saturated water moves upwards and forms the diapir as salt recrystallizes as it moves up. So I guess essentially the interaction of the water table and the rising salt structures.
No, I don't think I haven't, actually. I haven't seen a lot of literature on this, and I have to admit it's something I did not consider. So the idea, yeah, I would like to get, if you want to, you can send me maybe a few papers describing that, because I think it's a process I don't know much. Yeah, so feel free to email me, and actually I would like to deepen the question a bit more. Yeah.
Nice one. We have a few more. Congratulations. Carlos says, thank you for the presentation. Khan Sevki Kavak also says thank you, as does Barry Hanafi. They all enjoyed your presentation. We have two final questions. One is from Tunis Hain. And he asks, or they ask, how young could the normal faults be? Are they sin salt in places? And he says he can see some inversion is clear in some structures.
How young are normal faults? Yeah, we definitely put them as young as Messinian, so upper, because we can see them already deforming and affecting the thickness of the upper units. And clear sign of inversion. Yeah, I think we showed this nice pressed faults locally, or I don't know if it refers to something else. Yeah, but for the edge of the fault, at least from the slide where I am here, or you can see also this one here, definitely. No, sorry. On the promontory here, we definitely see that there is activity already during the Messinian. Then I think there are faults that might be activated only during the moment where you form this, where you buckled your overburden. To say that for sure, I think the ideal would be to have 3D and see how these faults prolongate in 3D on the surfaces, and that we could have a better insight maybe on whether they were already here before the inversion or if they purely formed during the inversion.
Nice one. And then our final question is from Rafael Urbina, who says, great presentation. Their question is regarding your seismic reprocessing. Was it done pre or post stack migration, and which software did you use?
Yeah, we did everything pre-stack migrated. That was the whole idea of the beginning of the project, to go from post-stack to pre-stack. I did it pre-stack migration and pre-stack depth migration. Here I presented in this paper only the depth migrated section, pre-stack depth migrated section. And the whole processing was done on Reveal from Water, whom I thanked at the end of the presentation for providing it to us academically, so free of charge. Yeah. And I would, if I may advertise, recommend it for processing. It was very nice to process. I have an experience with different software, and I really enjoyed using this one.
That's one. I guess that's all our questions. So from myself and the team at APG, Salt Basins, thank you very much for the really interesting presentation, Simon. It was, I guess it's an area we don't usually get to see. So thank you for sharing your work.
Yeah, excellent. Thank you, Simon.
Yeah, I guess for everybody in the call, we'll see you all in 2 weeks' time. Our next talk is on the 28th of April with Maureen Lartigo, where we'll be going to the Sivas Basin to look at some cool salt tectonics over there. And if you want to catch up on Simon's excellent talk again, this should be live on our YouTube channel in about a week or two. So yeah, thank you again, Simon. And
yeah,
look forward to seeing the rest of the papers that come out of this work. It looks really cool.
Yeah. All right. Thank you, everyone. Have a nice evening, morning, day, wherever you are.
Bye, Simon. Thank you.
Great. Thanks, everyone.